So yeah, thank you all for coming. I'm very happy to get to introduce Eduardo today. And Eduardo, thank you for accepting the invitation. So Eduardo worked, well, he got his PhD from the Max Planck Institute in Germany. Then he did a postdoc at the MIT. And then he came and joined us at the BSc in 2018. He also he's also a part-time assistant professor at the UPC, it's the Polytechnic University of Catalonia. And he was involved in multiple European projects. He worked on Applicate, which is a European project which linked the polar climate with the mid-latitude, look at the interaction between the two. But today he's going to talk about the work that he did in the PRIMAVERA, which look at the impact of increasing horizontal resolution on in the climate models. So I worked with Edu for a few years while I was at the BSc. So yeah, again, I'm very happy that he accepted to present. And I'll just say that one of the best things I ever did as a group leader over there was convince him to join us. So yeah, Edu, thanks again. And you have the floor.
Thank you, Lee, for the introduction. For the invitation. It's very nice to be here. I'm gonna share my screen and we can see my slides. Can you see them?
Yep, very well.
Okay. 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 Well, good morning, everyone. Thank you for joining. I've seen many people connected, so it's very exciting for me to present these results to such a big audience. And as Lee mentioned, these results are part of this big European project named PRIMAVERA, which dealt with the benefit of increasing model resolution in many aspects of climate modeling. And so I have to, you see many names here, but the project involved many European partners and all the researchers behind. I should be thankful to all of them, to those who got the money, who designed the project, designed the simulation, ran the model, so did the analysis. So a big thank to all of them. And yes, so I'm gonna concentrate on two different aspects of the benefits of increasing model resolution in global models. The first one is biases, and the second one is climate change. And when it comes to biases, we know that many climate models have biases in especially in the Kabul setup. Many of them are very well known. We have the cold North Atlantic bias, the warm bias over the upwelling regions in the eastern subtropical oceans. I should mention that the figure is biases in the simulations on the PRIMAVERA model. So we will see this figure again in a following slide. Other biases that we will know are the double ITCZ, the double intertropical convergence zone, where we have dry biases at the equator and wet biases on the opposite sides. And these biases have persisted over model generation. So we have if you look at CMIP 5, CMIP 3, CMIP 6 models, and you see similar biases in temperature and precipitation. So the question is whether we can get rid of these biases by simply increasing model resolution, or we need to do something else. We need better physics, we need more tuning. There are good examples in the literature where we can see that by increasing the model resolution, we can reduce the biases. This study in using the MPI model, they found a reduction in the warm biases, or warm bias over the upwelling regions in the eastern subtropical ocean by simply increasing the atmospheric resolution. but of course, it doesn't mean that the bias gets completely reduced. It persists even at high resolution. And it's not that it not always happens for all the models and for all the resolutions. So this, even though we have some examples, it's not clear that we can, this is the solution, that increasing the resolution, the model resolution is the simple, the easy way. So what I'm gonna do in the first part of this talk is to check the biases that we have in 5 different models that participated in the PRIMAVERA model. They have 2 different configurations. Usually the traditional 1 degree resolution in both the ocean and the atmosphere. And we have a quarter of a degree in the ocean and much finer atmospheric resolution at high resolution. And for one particular model, the one from the Met Office, we have a model that is 8 degrees. So it has nearly 1.1 degrees in the ocean. Comparing fully coupled and atmospheric only simulations, and I have to say that the idea here is that we see the improvement because of increased resolution only. So there is no additional tuning between resolution. So they share the same physics or nearly the same physics. And the negative side here is that we have 4 models that have a single model version for the ocean, in this case, the NEMO model, even though they have different versions. And 2 of the models have the same atmospheric model, even though the version is different. But again, so this sample size is not very widespread, but we can still try to see the improvement because of increased resolution. So starting with the biases in the temperature at surface, this figure is the one from before. So we have these well-known biases in temperature, and we see some improvement when we increase resolution. But also some degradation. So for instance, in the North Atlantic, in the South Polar regions, we see a reduction of the cold bias in the ensemble mean, but warming or warm bias of the Labrador Sea. So all these regions get warmer when we increase resolution. In other regions, we see some improvements as well. For instance, here in the upwelling regions, but they are small. In the atmospheric models, we don't have big biases in temperature because of course we observe SSE. So there is no biases at high or lower high resolution, and there is no changes between resolutions. When we look at precipitation, things get more or slightly different, because it's true that the double ITCZ bias that we saw before gets reduced when we increase resolution. So weather equator and dry tropics is the difference between the 2 resolutions. But in the atmospheric only models, and still in the coupled models, the biases are very persistent. We don't get rid of the biases just by increasing resolution. There is a big wet bias here over the Eastern Pacific region and all the tropics, that it persists at high resolution. And a similar thing we see for the cloud biases. So here is even more discouraging, because it doesn't matter whether we have coupled setup or atmospheric only models, or whether we have low or high resolution, the biases are the same, and the biases don't change with resolution or couple. You see the four patterns are really similar. So this is telling us that it doesn't matter what we do with resolution, the cloud biases won't improve. And there is some perhaps negative but also interesting aspect here, is that we have a wide variety of results when we look at individual components or individual models. Sorry. So we have, for instance, in temperature biases, we have a model that goes from a big cool bias here to much reduced bias models where the biases are slightly reduced but not much, biases models where there is some interesting improvements, but there are big differences between the models. So, and this complicates the analysis because we don't know whether it's because we have an increased atmosphere or ocean resolution, or it's because we have an increase in an improved coupling, or mm, we don't know whether this is related to small changes in the model physics. And we said we don't change physics, but actually when you increase resolution, you need to make some decisions about how you treat the physics, for instance, of the ocean mixing, because you go from a regime where you don't have eddies to a model that start to reproduce or start to resolve some eddies. So you need to do something with the eddy mixing. And some models switch off the eddy parameterization, some models keep them on. So these subtle differences might mean big differences for biases too. So there is a lot to do with biases here. But I'm gonna highlight here the meta-office model, the HATGEM3, because it's one of the best improvement models among the ensemble. It has substantial improvements in the upwind regions of, in the with the South Pole and North Atlantic. Also, in the double ITCZ, we see interesting and big improvements, for instance, here in the Atlantic region. But I mentioned at the beginning that for this model in particular, we have two high resolution models. One with eddy present ocean with a 25 kilometer, and one eddy reach, and one model with an eddy reach ocean with 8 kilometers. And when we compare the two, we don't see big differences, right? So it seems like reaching the eddy reach ocean resolution doesn't bring much improvement to biases. So we have this question here: what is the benefit then of reaching eddy reach ocean resolution for the climate models? And from here on, I'm gonna focus on this particular question, because we find other benefits or other interesting surprises, not for biases, but for climate change. The benefit of resolving this ocean mesoscale has been shown in previous research. For instance, here, this study forced a very high resolution atmosphere model with an SST field that sees the mesoscale in the ocean, and a field that doesn't see the mesoscale in the ocean. And when they look at the response of the atmosphere, how many storms develop or how active is the extratropical cyclone activity in the North Atlantic, they see a difference. They see an increase, especially in the western part when they use this field compared to this field. So that suggests that for the ocean, for the subtropical cyclone activity, resolving the mesoscale in the ocean might be important. There is also evidence that we having a high resolution in the atmosphere is also critical. For instance, here we have study that forced a very high resolution atmosphere model with an SST from a future climate. And they did the same for a traditional 100-kilometer atmospheric model. And when they see the response of the climate, they see a much stronger response in the eddy kinetic energy, so a measure of the storm tracks in the North Atlantic, compared to the traditional 100-kilometer resolution model. So again, this suggests that apart from the ocean, the resolution of the atmosphere might also be important, and having a finite resolution might lead to stronger responses, or in another way, perhaps having low resolution models might be lower resolution models might be underestimated the response to climate change. For precipitation, there is also big changes in this study. So all these, they see an increase in precipitation over this region, and also the mean state get stronger when they use a final atmospheric model. In the CMIP context, there is also studies looking at how storm tracks and the jet stream might change in the future, because this is related to changes in precipitation. And they find that the CMIP ensemble projects an increase in the cyclone activity over the North Atlantic in winter, with an increase in the jet stream. But of course, we have to assume that having a high resolution in the atmosphere and the ocean might be critical for such responses. So we have here the question of how much can we trust these results, or to what extent these results might change if we have high resolution models. So again, and finally, how much can we trust future projection of CMIP models for winter precipitation over Europe? And this question is particularly important for many European cities, because they need to get to prepare and adapt for risk of floods in the future if precipitation is going to increase. And then, but how much, of course. We are going to address that. I'm going to address this question using the meta-office model that I highlighted before. And in this case, I'm going to use historical and scenario simulations until 2050. We don't go any further because running high resolution is very computationally expensive, and it's hard to get beyond, or it's even hard to handle all the data and storage the data. So 2050 was the period that was chosen, and we might get new simulation for a longer period in the future. For the Hudson 3 model, we are going to compare 5 different configurations. The LL is the one that has low resolution in the ocean and in the atmosphere, and that's the kind of the traditional 100-kilometer ocean and atmosphere. We have a medium resolution. We have a model with a high resolution in the atmosphere, but a medium resolution in the ocean. A model with a medium resolution in the atmosphere, and high resolution in the ocean, and one with the high resolution in the ocean and atmosphere. And we go from, in the ocean, we go from 80 parameterized to 80 present and 80 weeks regimes. And here I mentioned the number of simulations we have for the historical period and the future projections. And you see here that for the models with the highest resolution in the ocean, we only have one simulation for each, because they were very computationally expensive at the time. In terms of sensitivity to climate change, how much they're going to warm in the future, the 5 configurations show similar warming or similar trends in the future in terms of global warming. So the results we are going to see is not because one model is getting too much warmer compared, or excessively warm compared to the others. And I'm going to compare the period, the last 2 decades of each simulation with the reference period here for this circle between 1960 and 1980. I'm going to start looking at precipitation because it was a question we had at the beginning. So these are the anomalies in winter precipitation between the period 2030-2050 and 1960-1980. Before looking at the results, a few things to see from this figure. So for these 2 configurations here, and the MM, but this is not some here because I didn't have space, I'm gonna compare the ensemble means. For these two down here, I only have one simulation, so I only compare the simulation I have. There is some white shading masking anomalies that are not significant based on reading the calculation in a control simulation. So they are indistinguishable from unforced variability. And here on the higher resolution, I have a stippling that is masking anomalies that are the largest among all the simulations. So when you see here stippling, it means that the precipitation increase at the high resolution is the strongest among all the simulations I have. And well, it's kind of clear now that when you have the highest resolution in the ocean and in the atmosphere, you have the biggest response in precipitation over Northwestern Europe, the biggest increases. There are also large increases over the Gulf Stream region. And these increases are also here present when we have an eddy ridge model, but this model doesn't produce the increase in precipitation over Northwestern Europe. But another interesting thing here to notice is that depending on the resolution I pick, I have different responses in the precipitation changes. So if I do my projections with this model, I might get different answers if compared to whether I use this one. So it suggests that not only the high resolution might be projecting the biggest changes, it's also that the projected changes might be sensitive to resolution. I'm going to try to explain why we have this big increase in precipitation over Northwestern Europe, and I'm going to start to connect it with the increase, with the changes we see in the Gulf Stream. And I'm going to start with temperature. Yeah. Can you see? Oh, yeah. So before that, I compare the changes among all the simulations we have for the high-risk mean protocol among the CMIP 6 and also among an ensemble of simulation performed with Conférencier in the UK. And we see that the changes of these regions are the largest or are on the upper edge compared to all the other simulations. This one here, I think, is the Canadian model. And I think it has the strongest response among all of them. And so, yeah, I don't know the reasons, but it has big responses everywhere. But nonetheless, we see that for the common model with the highest atmosphere and ocean resolutions, we have one of the strongest responses among all the simulations. And that was when I connected with the changes in the Gulf Stream. Because when we look at temperature changes of the Gulf Stream region in the ocean at the surface, we see a warming in the higher resolution. And the warming is the strongest when you have high resolution in the ocean and atmosphere. This warming in the Gulf Stream is also present here in the in a model with a high resolution in the ocean, but medium resolution in the atmosphere. And I'm going to explain the reason of this warming in the latest slides. But I'm going to now compare the magnitude of this warming among the ensemble, because it's really much stronger than the warming that projects the other simulations. And unfortunately, the observations are not strong enough yet, so we don't know whether we are where we are exactly. I don't know whether it's not clear whether we are following the observed trajectory, or we are overestimated or underestimated the observed trajectory. But nonetheless, there are studies already looking at observations that have been pointing out that the warming of the Gulf Stream might be unusually strong, or at least in the latest decades. One paper is particularly recent from month ago or so, and they find that in observations that they find that the warming of the in the Gulf Stream ocean might be faster than everywhere else, or at least outside the Arctic region. And this warming in the Gulf Stream has also been simulated in other models. In this case, it's the GFDL model with an ocean that has a resolution similar to ours, and they increase the concentration CO2 concentration by 4, and they got also a warming in the Gulf Stream, much stronger than everywhere else. So there might be some indication that this warming might be happening or might happen, but of course we need longer observations of if we want to see the warming. Of course, if we don't, we might start to use carbon dioxide emissions. Nonetheless, I'm gonna explain why we think this warming in the Gulf Stream is happening. So I'm gonna look at the structure of the Gulf Stream, and what you see here is the Moreno gradient in sea surface height. So this gradient is very strong here because it goes from a warmer temperature here to colder temperature here. So there's a big gradient in the sea surface height in the region of the Gulf Stream current. When we look at this region in particular, and we do a solar average, we see the changes over time. And in this case, is the model with the lowest resolution in the ocean atmosphere, and you see that the gradient is much weaker. And as we increase the resolution in the ocean, and especially, and we increase the resolution in the ocean, especially, we see that the gradient not only gets sharper, but also changes over time. In low and medium ocean resolutions, the Gulf Stream position stays relatively changed, but for the heavy rich ocean, the Gulf Stream shifts north over time. That explains why we see the warming, because now there is an expansion, a northward expansion, so warmer water get in regions where colder water were before. How do we explain this? I'm not going to go into the details because this is sort of deep in the ocean, but people have connected this changes in the Gulf Stream to the weakening of the AMOC and the deep western boundary current. So when the deep western boundary currents weakens because of adjustments within vertical, there is weakening as well in the surface currents, and that allows the Gulf Stream to expand northward, and that means that brings warmer water into regions where you usually have much colder waters. Nonetheless, we have here the warming that we saw before, and want to try to explain the implications of this warming of the northwestern European precipitation changes that we saw at the beginning. And I'm going to explain the difference between this simulation and this simulation, because even though they have similar response to the similar warming in the Gulf Stream, they don't have similar changes over northwestern Europe eventually, especially in precipitation. And the first thing that we are going to look at is the changes in the eddy growth rate. So a measure of the development of the Extratropical cyclone in the North Atlantic and European regions. So, and again, we see the biggest changes in the model with the highest ocean and atmospheric resolutions. By contrast, when we have a medium resolution in the atmosphere by high resolution in the ocean, the warming doesn't translate. The warming in the Gulf Stream doesn't translate into increase in the eddy activity of the North Atlantic and Europe. So there might be something else apart from high resolution in the ocean. We might need high resolution in the atmosphere as well to translate the changes in the Gulf Stream into increased precipitation for the downstream. And we propose two mechanisms. One is based on increased diabatic heating, and the second one is based on an acceleration of the upper tropospheric jet. The first one is increased diabatic heating. Diabatic heating is the heating that happens because of cloud formation, water vapor condensation. So, when you have cloud formation, heat is released from the in the process, and that burns the atmosphere. But that has reinforced the low pressure system at the surface and the top here at other levels. And we think that this increased diabatic heating might be better resolved in storm fronts or when you have a high resolution in the atmosphere. And it's also connected with the Gulf Stream warming. The Gulf Stream warming is putting more heat into the atmosphere. So you have more heating, more heat in the atmosphere. So making more increasing the diabatic heating eventually. And so it's what we see when we compare the two simulations with the highest ocean resolution. We see that the diabatic heating increases much more over the northwestern Europe as well, but also over the Gulf Stream. And instead of seeing negative values over the South Pole and North Atlantic, we see no changes. So that suggests that diabatic heating increases more when you have a higher atmospheric resolution. And that connects the warming in the Gulf Stream to an increase in or an increase in the development of extratropical cyclone over the North Atlantic. As yes, we see an increase in turbulent heat flux in the Gulf Stream, so we can connect the heating at the surface with the heating in the atmosphere and the development of subtropical cyclones and increasing precipitation for the Gulf Stream. I mentioned two mechanisms. The other one is an accelerated upper tropospheric jet. This one I think is easy to understand because basically if you have a stronger jet, there's going to be a stronger shear between the upper levels and the surface. That makes your atmosphere more unstable, and that facilitates the development of extratropical cyclones. And perhaps, or we speculate that this might be when you have a high air resolution in the atmosphere, there's going to be an enhanced mean flow momentum transfer, and that's going to bring more momentum into the jet, making it faster. And this is what we see when we compare the two simulations with high resolution in the ocean. We see a faster jet in the one acceleration of the upper tropospheric jet in the simulation with the highest atmospheric resolution compared to the medium resolution in the atmosphere. And that's very well connected with the increase in the eddy growth rate we saw before. So the anomalies are very well played. So we have these two mechanisms explaining why the Gulf Stream warming eventually translates into an increase in precipitation from Europe. And this is because increase in heating and transfer of momentum into the atmosphere makes enhances the development of extratropical cyclones. And when you have more frequent or stronger cyclones, you might end up with stronger precipitation increase of Europe. Perhaps this should be the end of the talk, but I'm gonna highlight here two drawbacks from our study, because we know that we only use one model and one model realization. So we face criticism saying that perhaps your model is too sensitive, or you might be undersampling the variability. So that's why we gonna present the stream project. This is a new project we just got funded, and this is gonna produce new simulations to study or to test our hypothesis. So the stream project basically deals with, it's gonna study the benefits of resolving the mesoscale in the ocean for the North Atlantic Ocean circulation. Also, whether it affects the response of the North Atlantic and European climate and future evolution. And we are gonna have a part looking at predictive skill when you use high resolution in the high resolution models. We are gonna use our model here, the easier, and we are gonna use the 15 kilometer in the Atlantic Ocean, but also the lower resolution version. And this is collaboration with Meta-Office, the Max Planck Institute, and the University of Texas. And this brings me to my summary. So we started looking at the benefits to reduce biases. The increased resolution, we didn't see much benefits. We see a lot of some changes that were strongly model dependent, and we might need not only further model development, but also tuning or even reaching fine resolution in both the ocean and atmosphere. We also look at differences in the response to climate change when you have different resolutions and in your models, and we see differences in the response of the Gulf Stream and also further downstream of the precipitation of the northwestern Europe. And I finally presented the new project stream that is gonna explore the ocean mesoscale in the North Atlantic and the benefits for climate change and predictability. So thank you for your attention, and I'll be happy to take any questions.
Hey, thank you so much, Edu. That was very nice. Do we have any question for Eduardo?
Salut Louis-Philippe, j'en aurais une si tu m'entends, mais je ne sais pas comment lever la main.
Oui, je t'entends très bien, vas-y.
Okay. Okay, thank you for the talk. I just have one comment and a question. I just want to know why you didn't use the Eurocordex data when you assess the change of precipitation in the northwest of Europe, in addition to the GCM data that you have shown. And the comment is more on the first part of your talk. You have a lot of atmospheric model, but in fact, you have only one ocean model. And I know that you said that in your last part that it's a critics of your work because you have only like one model. But even for the first part, there's only one one ocean model. So how can you say that the changes that you've seen is not linked to some feature that is related only to the NEMO model and not to globally ocean model?
Yeah. So about the Codex data, I think that was the first question, right? Yeah. So we didn't use it. We got the suggestion, but we didn't use it. So it was simply the decision we wanted to focus on this particular model. But I think it's interesting, this comparison between regional model and global models, and especially because some of the changes we have seen here are happen in a region in regions that might be outside the domain of regional models. So if the regional models is using low resolution models for as a boundary conditions, and this low resolution model doesn't produce the changes, we shouldn't expect to see the changes inside the regional model because they are not triggered from outside. So So that, yeah. And about the second question, why we have, yeah, so for the NEMO model, actually there are two models. One is the NPI, the other is the NEMO. But it's truly, you're truly right. Perhaps the NEMO model is over represented in our ensemble, and the changes we see is because NEMO is a common model. Yes, so we hopefully we might use we will have more models from other centers not using NEMO, but because it was an European project and many European centers use the NEMO model because it's a European model, so we ended up having made perhaps too many NEMO models.
Thank you.
Thank you.
Yeah, yeah, those were the models that were in Primavera. So all the data were on the same machine, and those are the simulation we had access to when we did the study. So, yeah. Any other question? I have one from David Duar here. It says, should these type of resolution study also account for subgrid scale parameterization?
You mean the highest ones? I guess, yeah. Probably, we don't know. It's there is a question that what happens if we increase resolution and we find that mesoscale resolution is critical? Should we keep increasing resolution and resolution? So I guess that's we use what we can do basically, because computers are don't allow us to go beyond that yet. But
David, je ne sais pas si tu veux intervenir, spécifier ta question.
I guess what I mean is that traditionally use parameterizations to account for processes that are not dynamically resolved. And so when you start to resolve them, in principle, you need to take out some of this parameterization
yeah.
to avoid double counting some of these processes. So, and it's a bit of a naive question, but how do you make sure that you're not double counting effects from eddies when you're not adjusting the parameterization when you're increasing grid resolution? Hope that's clear.
Yeah. So it's actually, yeah. So that's one of the questions we have for the biases. So we have two models that switch off to eddy mixing parameterization when they went into the quadrilateral model, but two other models keep the eddy mixing, and one the MPA model changed basically the scheme. So and they have a big difference in terms of biases. So it's something to keep in mind, because those small differences in physics, that might be very important for biases and responses too. So I guess it's something that we need to keep in mind when designing high resolution models as well.
Yeah, if I can just add a bit of background. I mean, there was an intense discussion at the beginning of IResMIP and Primavera as to like what to do with the parameterization when we switch between resolutions. And like a big group of people just didn't want to touch it because they just want to look at the impact of resolution. And another group wanted to tune it separately to have a fairer comparison between the two. And in the end, they had to pick one, and they picked, we don't touch it. Mm-hmm. But the other option would have been equally valid. But then Hélène, you had a question?
Yes, thank you, Eduardo, for your presentation. Since the early beginning of my career, I was always wondering if with increased resolution, if what is resolved should be converged to the same feature or bias or whatever. So I am not surprised that you, on many features, you didn't see an improvement of the, or not much an improvement of the bias with increased resolution. But did you perform somehow, or are you planning to do so, a scale decomposition for your different resolution in the model to look at this resolve scale in both the model outputs and the observation? Because especially for precipitation, and there's a seasonality to that on the contribution from the large scale mechanism and much small scale mechanism. So at a 25-kilometer resolution, it's still a lot of parameterization and unresolved processes that are involved. So yeah, I was wondering if you perform a scale decomposition in your analysis.
No, we didn't. Well, there's some of the models have intermediate resolution, but you can see the benefits of increasing one or the ocean or the atmosphere, but we didn't perform that analysis. No.
Yeah.
But,
still with these improvement in resolution in some areas, I suspect that the contribution with even lower, smaller scale mechanism are probably dominant, and in those circumstances, you don't expect much of an improvement, I guess.
mm-hmm.
So, thank you.
Thank you.
Any other question for Eduardo? Going once, going twice. Right. Okay. I'll just have the final word then here. Just to bounce on Dominique's question at the beginning, where she was asking about the Cordex results, comparing with Cordex. I think, you know, we were discussing what we can do in Aerosmith 2, and this is the kind of thing that if we can facilitate would be great to have. So, I mean, here, yeah, we do have a, you know, a big difference between eddy resolving and non-eddy resolving simulation. So if we can somehow facilitate comparison between these type of simulation and Cordex, I think there could be a lot of low-hanging fruit and lots of studies that could come out of this kind of comparison. So, yeah, this is something to keep in mind, to keep in mind going forward. Aerosmith 2.
Yeah, I totally agree. Yeah.
And then before I let you go, so you've looked at Europe. Have you thought about North America also? The impact of eddy resolving on us here?
Not really. There is this big change in precipitation over the Gulf Stream that extends into the Eastern American coast, but not really. Not really. We didn't focus on all of the regions. I have we did a when I did the first analysis. I noticed the big changes of Europe, but not big changes over the Pacific. And I guess that might be because there's link between AMOC weakening Gulf Stream that is not happening in a similar way in the Crucial region, perhaps.
Okay, thank you so much.
Thank you.
Again.
Oui, Philippe?
Oui.
J'avais mis une question dans le chat. Là.
Oh, excuse-moi, je l'ai manqué. So sorry, I didn't mean to. Do you want to ask it?
Oui. Thanks for the presentation. I thought it was very interesting. I have a question regarding RCMs. Do I understand correctly that what you showed is suggesting that RCMs with just a higher resolution atmospheric resolution is not sufficient to reduce biases, and that we should aim for coupled RCMs with higher ocean models, higher resolution ocean models?
So these are global coupled models. So this is not regional models. So when it comes to forcing the regional models, the precipitation response, even for the global models, might be different depending on which model you pick, and if it's connected to dynamical changes, and the dynamical changes are different among resolutions. I'm not sure which one might be the best. Perhaps the idea is to use some of them, at least from 3 different resolutions, or you sample of the range of changes. But that's my suggestion.
Yeah, but that's one of the goal of using an RCM, that you have a higher resolution and you can better describe phenomena and have eventually reduce the biases. But that's not really what we obtained up until now.
Thank you.
Anybody else? Okay, then in that case, for real. Thank you so much, Eduardo.
Thank you.